Okay, last of these maps, and just a little bit of extra complexity once again. So in this case, we still have beds that are dipping at different angles, not in different directions this time, but in different angles. This same situation could actually apply to different direction beds, but in this case, they are both dipping roughly towards the west. So all the beds here are dipping towards the west, but the angles are different. So what does this mean? Once again, is this a fold or is this some kind of different situation? Now, this could be a fold. Sometimes you can get folds that have different angles, but all dipping in the same direction. That could be a fold that looks something like this. The beds that are dipping at 80 degrees, something like that, and then they join up, and then you have a fold that comes down at shallower angles like that. So that would be our 30-degree limb. So this would be a very asymmetric looking fold, but it's quite possible, and you do see these out in the field quite regularly. If you come out on some of our second and third year field trips, you'll see folds that do almost exactly this. So if we had our horizontal along like that, that would be 80, that would be 30, and so that would be a fold. So is this a fold? Well, actually, no, this is not a fold. And the reason we know this is not a fold is, unlike the last situation, we don't have that repetition of beds. Here we have a sandstone and then a conglomerate. Then we have three other units, and I haven't got the key loaded up, so I can't remember exactly what they are. This looks like limestone and shale and something else maybe. So we've got completely different units. We have no repetition. So unlike the previous map, where we had this nice repetition across this fold, where we went sand, limestone, shale, conglomerate, conglomerate, shale, limestone, sand, now we don't have that repetition at all. So we're not dealing with a fold in this situation. So we've got something else going on. So the next thing is to try and figure out exactly which units are older and which units are younger. And here we can see that these units look like they cross the boundaries of the other units. So that's indicating that these units here are on top of those other units. So these are the younger units. They're sitting on top of these ones because you can see they're crossing through this boundary here. So we've got those units being older than these other ones that are lying beneath. If you look on the key, you'll see that this unit here is an igneous unit. And again, I can't remember exactly what it is. It's a granite or something similar to that. And around the edge here, we have a contact aureole. Contact aureoles are metamorphic rocks that come from this thermal metamorphism or contact metamorphism. When you have an intrusive rock, this rock, if it's a granite, was probably something like 700 degrees Celsius, and then it's intruded into these sedimentary rocks. These were probably something like 100 or 200 degrees Celsius, and so you've added a lot of heat to these rocks, and that causes this metamorphic effect. So this metamorphic aureole is a metamorphosed version of these sedimentary rocks as a result of the intrusion of this granite into this body. And so once again, that's telling us that this granite is younger than these rocks around it because it's metamorphosed those rocks. So those rocks must be there first. Also, when you have an intrusive rock, you need it to intrude into something. So this country rock, this material around it, had to be there before the granite. So these rocks here are the oldest rocks. These sedimentary rocks are the oldest rocks. Then this guy, and then these things that are sitting on top of it. So once again, we draw a topographic profile, which in this case is flat, and then we line up our piece of paper along our line like that, and we make marks where each of those boundaries are. So we have a boundary there, a boundary there, a boundary there, a boundary there, and a boundary there. Now we also need to figure out what's going on at depth here, and we simply infer that what's happening underneath this conglomerate unit here. Well, let's just infer that we've got a nice continuous, we're just really extrapolating the two dots between those lines. And same with this unit here, this probably continues through like that because that's what all the other units in the area are doing. So this is an inference. We don't know that this is exactly what's going on, but it seems like a pretty fair assumption that they're going to be continuing on something reasonable like that. And it's always possible that this unit actually shoots out like that, but we don't know. And I think a fairer, more reasonable sort of interpretation would be that it's continuing around like that, and this unit is coming down like that. So we can mark these onto our piece of paper as well. and then we transfer that material onto our cross section. So once again we draw up our box like that. Again, all of these, I should have noted, all of these are at VE equals 1. And like I said in the lecture, in the practical class, almost all geological cross sections you ever see are going to be at VE equals 1. If you do this at VE equals anything else, anything but 1, so if you did it at something like 5, then you have to recalculate all of these dips because you're stretching it, and that's causing the dips to actually change. You take something like this that's dipping at 30 degrees, as you stretch it in this sort of direction, your 30 degrees might look something more like that, and you can't measure that with a protractor, so you have to recalculate the angle that you need to draw on. So generally we do these at VE equals 1, so our horizontal scale and our vertical scale are the same. Make sure you got all your labels, put your key on there, title on there as well. These are things that should be on every cross section. Okay, so that noted, we've now put our topographic profile on, which once again very conveniently is perfectly flat for us, and we go along and mark each of our unit boundaries on there that we took off our piece of paper, and then we start drawing things on. So generally the easiest ones to start with are the youngest things because they cross-cut everything, so they're going to power through all the other rock units on the map. So might as well draw those guys on first because they're going to be nice continuous lines. So we'll draw on these guys first. So that was nice and easy. The next thing to draw on generally is the intrusion. So basically going to the next youngest thing. Now with the intrusions, once again, we don't know exactly what the boundaries of this intrusion are doing. Remember with sediments, sediments are deposited flat, and then we can have processes that cause them to tilt. So we might tilt them like this, or as we saw before, you might even fold them like this. Intrusions don't start off flat, they're coming from somewhere deep within the earth, and they generally have quite irregular sorts of boundaries, and we don't know simply from the map. You'll see there are no measurements on here, we don't know what those boundaries are doing, so once again we simply have to infer what those boundaries are doing. So the easiest way to do it is simply infer they're coming straight up and down. Intrusions come from below, so generally that's a reasonable sort of assumption. They have irregular boundaries, so I draw them normally as a jagged sort of line going down like that, and our contactorial is actually going to mirror what the intrusion's doing, because remember it's the heat from this intrusion that's causing that contact metamorphism. So we have these boundaries just going straight down like that. It might not be doing that, but remember this is a predictive model, so you're using the information that you've got to come up with a model. It might not be 100% right, that's why you might go out and dig pits or start doing drilling or something like that to test these models. So this is our best bit of information so far. That's what we're going to draw it as, going straight down to down like that. So once we've got that on, then we can start drawing in our last three units, these things that are dipping at 80 degrees. We've got one, which we'll have marked on our piece of paper. It's at the surface of the earth. It goes down until it intersects that intrusion. Remember the intrusion came after this, so it's going to cross-cut that. So it goes down and it stops where that intrusion is. So here we have our shale or something like that. Here we have our limestone or whatever that unit is. Then the last thing to draw on is this boundary, which we inferred before as coming through in a straight line like that. It's a reasonable assumption because all our strikes are going in that direction. So it's almost definitely going to come straight through like that. So that unit was something like up here. It doesn't come through this unit because this unit is cross-cutting this one. So we have to realize that it's not going to exist here, but it does exist underneath that unit. Where that unit stops, it exists and it goes down once again at that's 80 degrees downwards. So these guys here are 30, 30, that in there is 80, and that is also 80 degrees going downwards, whereas the intrusion goes more or less straight down. So don't forget all the other things you need to have on these cross sections: key, title, scale, height and meters above sea level, and then you've got a pretty nice geological cross section. So the last thing I've drawn on here is I wrote U along here. Now I can't remember if you guys will know this from GL 110, but this is what we call an unconformity. There should be notes about this in your mapping notes that I've put up on Moodle. This is an unconformity. This indicates that there is time missing. So there is a time gap here. There's been some kind of erosion and then these sediments have been put down. And in this case, where the unconformity is at an angle, so we have a difference in angle between these 80-degree units and these 30-degree units, that's a special type of unconformity called an angular unconformity. There are other kinds of unconformities, and again, they're outlined in your notes. This is a very important geological concept, so do make sure that you read through those notes and are comfortable with what an unconformity is and recognize why this one is considered an angular unconformity rather than, say, something like a nonconformity or a disconformity or a paraconformity. And what those are is once again outlined in your notes. So here we have an angular unconformity, and it's very useful to include that on your geological cross-section. So that's all of the geological cross-sections for exercises 1 to 5. If you have any questions, it's probably best to ask in the forums and I'll try and answer them there. Okay, thanks guys.